Welcome to Lecture 26, entitled The Divergence Theorem. And in this lecture, we're going to try to apply it in the 3D case for a specific application. The material covered in this lecture comes from reading Assignment 5, Section 3.2, specifically a problem involving cylindrical geometry, and Section 3.5 and additional example problems in Section 5. So objectives are basically the application of the divergence theorem for electrostatics problem. And the concepts and visualization skills are determining the direction of the field and the functional dependency of the magnitude of the field, and to develop the procedure for determining the field for a cylindrical symmetry example. So as usual, the outline is just a summary of the slides to follow, so we'll just skip over that. All right, so this is an electrostatics problem, which is an irrotational field problem. An irrotational field problem means that we're going to apply a divergence theorem. So if you look at the right-hand side here, this is the left-hand side of the divergence theorem. This is the right-hand side. But divergence of F, as we've shown earlier, will be just rho dV, integrate over volume. So this is the volume enclosed by this surface. And so it's this rho that would be given. So if we look here, this is from last lecture, we said that typically we can express an irrotational example either in terms of a displacement field D or an electric field E. And it's just a matter of the right-hand side taking on a slightly different form as you've seen here. To make life easy, we're just going to use D and we're just going to give it the generic symbol F. And so we're more or less talking about the divergence of F being equal to rho and the curl of F being equal to 0. So that's what you see over here on the right-hand side. And again, rho E is going to be rho. So the problem statement is: consider a cylindrical hollowed out rod of infinite length with inner radius R1, outer radius R2, aligned along the z-axis. The rod has the following charge density distribution rho. So for a radius between 0 and R1, the charge density is 0. Between R1 and R2, the charge density is rho naught, but it takes on a constant value. And if you go in excess of the R2, then the charge density goes back to 0. So it looks more or less like a shell of finite thickness and a uniform charge density in the shell itself. Note that because we're dealing with the cylinder, that the radius of the cylinder is just the square root of x squared plus y squared. So just make note of that. All right, so what is going to be the calculation procedure to compute F? 5 steps. First of all, we need to determine the nature of the symmetry and determine if superposition applies. Secondly, we have to establish a mathematical form of F and establish what we call the Gaussian surface. The Gaussian surface is associated with the left-hand side, namely the shape of the closed surface. Then we compute the left-hand side of the divergence theorem, followed by the right-hand side. We equate the two, and then compute from that the field F. Okay, so the first step is to establish the symmetry. And you may wish to click on the following link where you can investigate the characteristics of this geometry. The slider T, which is here, is the observation point on the expanding orange shell. So that's this blue point that you see here. As the shell expands, this blue point moves out with it. Slider S basically is a moving point source pairs along the circumference of the blue shell, so that these 2 points in tandem would rotate either to the left or to the right around this specific shell here. These correspond to point charges. Of course, this whole surface is peppered with point charges, but we're taking just 2 in particular, always in the form of pairs. It just makes it easier to analyze the system. And slider P is the movement of point source pair on the blue shell with respect to z equals 0 plane. So that basically means that we're taking this point, moving in the z direction, and at the same time moving this one in the minus z direction, so that effectively the distance between z equals 0 and this point and z equals 0 and this point essentially all remains the same. Now, the reason we're doing that is because you can see clearly from this, for a given shell, if we take this charge, point charge, and this point charge, then the field from this source would be pointing in this direction, and the field in this source would be pointing in this direction. If you then take these two and superimpose them, that means add the two vector fields, you get cancellation of the component in the z direction, and you only have the field component pointing in the r direction. So for every pair that you have moving it up or moving it down, you always end up with contribution only in the radial direction. Now, if I move these 2 points around the circumference in the blue, all that would happen is I would move along with the surface, and the field would be pointing in the radial direction. So if I had 2 dots here, the field would be pointing outwards, similar to shown here. And if I were to move up and down an infinite cylinder, the picture would not change. And so what we can say from this is that the field only has a radial component, although how it depends on radius is in fact what it is that we're going to be trying to determine. The orange shell that you see here is typically called the Gaussian surface. It's at least a portion of the Gaussian surface, and it's a portion that's allowed to expand or contract as we try to map out what happens to the field as a function of radius. And the blue is just an arbitrary cylindrical surface. This could be a volume, and we're just taking one slice out and just taking 2 point sources and basically creating this vector field showing that the field can only be radial. We could take another blue shell, a smaller diameter. We end up basically with the same picture. Basically, conclusion is field only has a radial component, and its magnitude depends only on the radius, and it's how far out this orange shell is with respect to the axis of symmetry. All right, so the equation of the field F and establish the shape of the Gaussian surface. So we know that the field is in the radial direction, so we can write it in Cartesian coordinates to look like this. And we know it depends on the radius, so we say it's a function of square root of x plus y squared. However, square root basically is greater than or equal to 0. So there's a chance that the field can be pointing inwards or outwards, and that's accounted for by just changing the sign on the unit vector. So this is for a field pointing outwards in a radial direction. This is for a field pointing inwards in a radial direction. So what we need to do now is to create this so-called surface that we're going to use to compute the actual field itself with the magnitude. So the closed surface, as I said, was associated with the left-hand side of the divergence theorem. So now the question is the criteria for choosing the surface segments in the first place. It's clearly related to symmetry, but as far as the vector field is concerned, we want to make sure that the vector field F is either parallel to and uniform along the surface segment. And as I said, we will have 3 segments to create a closed surface: an exterior cylindrical shell, a top circular shell, and a bottom circular shell. And so we want to make sure that we're either dealing with fields that are parallel to surfaces or perpendicular to surfaces, as shown in the second bullet point here. All right, so this surface that we've chosen in the case of cylindrical symmetry basically achieves both of these objectives. And so we create a cylindrical shell surface with a variable radius r, because we want to probe how the field will change as a function of radius, and a top and bottom circular surface. So the left-hand side of the divergence theorem would be closed surface integral, but because there are 3 separate surfaces that comprise the total closed surface, the outer cylinder, the top surface, and the bottom surface, right? These 3 summed together represent the closed surface. Now, the field we said was pointing in the radial direction, whereas the top surface is pointing in the z direction, and the bottom surface will be pointing in the negative z direction. Recall that with the divergence theorem, the surface area vectors must point outwards from the surface. But the field being radial and the surface being in the z direction means that these 2 are orthogonal to each other, and these 2 are orthogonal to each other. Therefore, their dot product will be equal to 0. And therefore, the only one that makes a contribution to the closed surface integral is this one. And luckily here, the field and the surface area vector are going to be in the same direction, parallel to each other. Therefore, we can essentially say that the closed surface integral f dot ds is f dot n1 ds. n1 basically representing the surface area associated with the outer cylindrical surface. All right, so this is just an interactive visualization of the Gaussian surface that you can play with. So what T basically does is expands this red, right, which is the Gaussian surface. It basically moves in and out. This basically represents the inner radius of the charge distribution. Nothing in this region. Here the charge distribution is constant, and exterior to this the charge distribution is 0. Outer radius being R2. I've labeled the surface area vectors. This was the upper surface of the Gaussian surface. This was the cylindrical surface, and then below there's another one that's pointing downwards. And so what we're doing is we're expanding the radius of this Gaussian surface, and we're constantly checking to see what is happening on the inside, because the surface is enclosing a volume, and we're interested in the total charge enclosed within the volume, and that volume is enclosed by this, what we call Gaussian surface. The vector fields are shown here to be in a radial direction, the ones indicated in blue. And the height, in this case, basically, that we've chosen is just an arbitrary value of capital Z to essentially work through the divergence theorem. So now we compute the left-hand side of the divergence theorem, which is basically the integral over the surface area of the cylinder. The field we know is radial, and we know that it depends on the radial position, and so we've basically written it out in this form. This is just a Cartesian representation of a radial vector field in cylindrical coordinates. R is just the square root of x squared plus y squared. So we need to determine the differential surface area vector. So first thing to do is to parameterize the cylindrical component of the Gaussian surface. And to do that, we just let x equals r cos theta, y equals r sine theta, and z equals z, and theta ranges between 0 and 2 pi, and z ranges between 0 and capital Z. The position vector that sweeps out points on the surface, therefore, is r cos theta, r sine theta, z. And so next step is to compute basically the partial of r with respect to theta, and the partial of r with respect to z. In doing so, we end up with these two vectors, t theta and tz. Next step is take the cross product of these two vectors, which means we just set this up as a 3 by 3 matrix. First row is the unit vectors, second row is the first vector, t theta, and the third row is the second vector, tz. If you compute this determinant, you'll end up with this result, and this vector points outwards from the surface, so it's in agreement with convention that the surface area vector always point outward from the surface. So n1 ds1, which is the surface representing exterior cylindrical surface, is t theta cross tz, d theta dz. Putting it together, we end up with this expression. F now has to be evaluated, given that we've parameterized according to theta and z, and so x gets replaced in this expression by r cos theta, y gets replaced by r sine theta, and z remains the same. And so we end up basically with this expression, and which simplifies to this. So f of r comes out as a constant, depends only on the radius. All right, so now we can compute the left-hand side of the divergence theorem, and there's only one surface that makes a contribution to the flux, and that's the exterior cylindrical surface. So making use of the results from the previous slide, we can substitute in for f and the differential surface area vector. So the dot product is shown here. If we do the dot product between these two, we end up basically with just r d theta dz. This is basically going once around the circumference, and this is the length of the cylindrical shell from 0 to capital Z. If you perform this integration, f of r, of course, is neither a function of theta or z, it can come outside the integral sign, and so we end up with this expression, which is unique to an object with cylindrical symmetry. Now, for all the different geometries we'll be considering in this course that apply, so have symmetry, namely planar, cylindrical, and spherical, you just need to compute the left-hand side once, only once. Secondly, in a test setting, a derivation for each geometry is not needed. Rather, we just need a short explanation as to how the left-hand side came about, and just to show that you understand how the left-hand side basically was derived in a very short form. All right, this table just is a summary of the three different geometries we'll be considering. The cylindrical case we've already just discussed. For the planar case, for example, you have a slab or sheet in the xy plane, the zy plane, or xz plane. These are three possible planes to be considered. And the Gaussian surface in all cases is a six-sided rectangular box. For the case where we're dealing with a slab or a sheet which is parallel to the YZ plane, you'll find that only two surfaces make a contribution to the flux. And those, if we're dealing with 2 points exterior to the slab or sheet, then we can essentially make the following statement, that the total flux is just the sum of the two contributions on either side of the slab or sheet, and it turns out f of x2 is equal to fx1. And so we don't have two to worry about. We actually have this constraint, and therefore we're only solving for one and immediately obtain the other. We could also have it parallel to the xz plane, in which case this becomes a function of y, or it could be parallel to the xy plane, in which case these become a function of z. But again, under these conditions, we find that if we're exterior, the points are taken, the sides of the Gaussian surface are exterior to the slab on both sides or sheet, then this condition basically is satisfied. These two are equal to each other, so you only have to solve for one of them. For the spherical case, we end up basically with the flux integral being 4 pi r squared f of r being the radius of the Gaussian surface, and f of r, of course, is a scalar function that's to be determined. So just two notes. For the planar geometry, there are two surfaces which provide a non-zero contribution to the flux, which is what we just mentioned. And secondly, the expression above assumes that the vector normal to the Gaussian surface is in the same direction as the field. All right, so we basically to make these things consistent with each other. All right, so now we can go ahead and compute the right-hand side of the divergence theorem, which means we're integrating the charge enclosed within the volume, which is constrained by the Gaussian surface. And so originally the problem is that of a cylindrical shell of a certain thickness, an inner radius r1 and outer radius r2. And so because we have a discontinuity in the charge density profile, we have to consider these as three separate regions. So the region from 0 to r1, in which case the charge density is 0 because you're inside the innermost radius. And then when we sweep through the region between r1 and r2, there is a charge density, right? And thirdly, when we're exterior to the cylinder as a whole, which is at r greater than r2, then we have no charge in this region that makes a contribution. And so there's three separate integrals to be considered. In the first case, the charge enclosed, if the Gaussian surface has a radius less than capital R1, will be 0. Between R1 and R2, we set up the volume integral such that basically we're computing the total charge enclosed from 0 to z. The innermost radius that we'll be considering is the inner radius, just as we penetrate the Gaussian surface inside the object, that is between R1 and R2. All right, and this extends to some arbitrary value of R, right up until you reach the outer surfaces when R is equal to R2, but no further than that. And again, because we're going once around the circumference, it's from 0 to 2 pi. So this integral basically computes the total charge enclosed in just this region between R1 and R2. We also have the additional charge contribution going from 0 to R1, but it was 0 from the previous step. So when we add these two together, you do this integration, we end up with this expression. For the third case, which is when R is greater than R2, which means the Gaussian surface is outside the cylindrical shell, that's R is greater than R2, then we know that this integral here, when extended up to R2, is the maximum value of charge enclosed that can be obtained. The moment we go outside that region, then essentially from R2 and onwards, you get a 0 contribution because there's no charge in this region. And so effectively, we end up then with a result that is similar to this, except that R basically just becomes R2 squared. And so these are the three different regions that need to be considered when we're computing the field. All right, so for 0 less than r less than equal to 1, the left-hand side was 2 pi r capital Z f of r. In fact, it was the same irrespective of what the radius was. So we've just put them all in here for sake of argument. As far as the right-hand side was concerned, in this region it was 0. In this region it took on this value, and in this region it took on this value. And so now what we have to do is basically compute FR, and in this case FR equals 0. If we divide through by 2 pi RZ, we end up with this expression for FR. And if we divide through by 2 pi RZ on this side, we get this expression here. So the next thing is to put it in vectorial form. These are the magnitudes. So in this area, it would be 0 r hat. In this region, it would be the expression shown here, r hat. And this region, it would be this expression, r hat. We can now basically graph the result just to see what it looks like. And we have an expression that looks like this. So notice in this region up to R1, the field is 0. Then it rises as it's moving through a region where you have constant density until it reaches R2. And then beyond this point, the field takes on a different form, has this shape, and comes down like this. The values that I used in the example are shown here. Rho naught, which is a constant, was taken to be 10. R1 was taken to be 0.3, and R2 was taken to be 1.0. That concludes lecture 26. Thank you for listening.